everyone, welcome to the ninth video of Module 7, and here we are going to derive the equations for the backward propagation. I'll be showing you the PDF of equations. I'll take you through each and every equation and help you understand that how exactly did we get this particular equations. So let's get started. So let us first start with the revision part. Over here I am having the data that I'll be using in my architecture. This is the architecture that we have designed, with the shapes of the inputs being 4 cross 2 because there are only 4 rows and there are 2 different columns, so the shape is 4 cross 2. And then if I talk about the weights, there will be 2 from the inputs and the 4 from the hidden. So in between X and H, the total connections will be 2 cross 4. And therefore the shape of the WXH will be 2 cross 4. And similarly like this, the weights shape between H and Y will be 4 cross 1. And then what about the output over here? The shape of the output will also be 4 cross 1. After that, these are the equations that we have for the forward propagation, where it's really important for us to know that these equations are not only the equations that we always have. It always changes depending on how much changes we do in this architecture. So for now, because there is only one hidden layer, there will be 2 outputs because of this hidden layer. First, the inactivated output, and then the second one will be the activated output. Just like that, in the next layer, there will be one inactivated output and one activated output. And that's exactly what you can see over here, that the Z1 is the output over here that is not activated, which is simply the multiplications of your inputs with the weights. I am not considering biases anywhere, as you know, because that's my choice if I want to have it or not. Currently, we are not having it. But yes, after that, I'm going to activate it with the help of the sigmoid activation. And then those outputs are going to be acting like an input for the next layer. And over here also, first you will get the inactivated output that is called Z2, which is the multiplication of the activated values over here from your first layer. And then multiply that with the WHY weight vector or the weight matrix. And then you are multiplying them. Again, I'm not having the bias. That's your unactivated output at Z2. And then to activate it, again, I'm using the sigmoid. Now the important part is the shape over here. I know that if I'm using the matrix multiplication over here, so that I don't have to do this manually, x1 into w1, x2 into w2, so on and so forth, this does that thing automatically for me. So over here, if I look into the multiplication part, the column of your x should match with the row of your wxh. And because they are matching, the matrix multiplication will happen successfully, and the output will be the rows of your x and the columns of your wxh, that is 4 cross 4. After this, in your A1, because you're not trying to multiply this or do something else, we are just transforming this 4 cross 4 values into some different values, then the shape is not really going to change. After that, for the Z2 part, this one, which is unactivated output for your output layer, over there also, if you are going to have this kind of matrix multiplication, you need to know that A1 is going to be, that 4 cross 4, and WHY is 4 cross 1. And therefore, matrix multiplication will happen successfully. And the output of this will become what? 4 from A1 and 1 from WHY. And the final is 4 cross 1. And then if you are going to just apply the sigmoid activation on top of that, the output will still not change. It will be 4 cross 1. So these are the output shapes that we know about in the forward propagation and also the equations of the forward propagation. But now the important part is the backward propagation, how this kind of equations are going to be there. So over here, you know that even from, I guess, the linear regression session, I've already helped you understand how the derivative works and everything. So over here, what we are going to consider is that this is our cost function. So what is the derivative of this cost with respect to your output? That's what you have to find, right? So not with respect to your output, but with respect to your weights and biases. Over here, we don't have the bias. So over here, I want to find out what's the derivative of this cost with respect to your WXH and WHY. And then I'll be using that in my gradient descent, or to be honest, any kind of optimizer that you're using. But over here, because we're using gradient descent, so yeah, I'll be substituting this derivative of cost with respect to WHY and WHX into its respective equation of the gradient descent. But now, if I talk about how can I get the derivative of this cost with respect to first WHY, and then how do I get the derivative of the cost with respect to your WXH? For this, again, we need to follow this chain rule. And how the chain rule is going to work? First of all, to reach to this particular point, I need to take the derivative of the cost with respect to your y cap. So after getting to the y cap part, I'll need to take the derivative of y cap with z2. Once I reach to the z2, I can take the derivative of z2 with respect to why. And that's how I'm going from j till why. So if I form the relation, that's something that you are seeing over here. That the dj dw hy, this is actually your dj dy cap, which is nothing but the derivative of this cost with respect to your y cap. Then derivative of this y cap with respect to z2. And then derivative of z2 with respect to your why. And now, because you are also aware about the derivatives, and if you do this kind of derivatives, the 2 is going to come down, and then it's going to be 2 by n multiplied by this particular thing. But now over here, it's your choice, 2 by n, if you want to keep it or not. It's simply going to act like some kind of scaling factor. So that's what I would not consider to add over here. But even if you consider it, there won't be any problem. So if you have this thing multiplied by 2 by n or without 2 by n, the outputs will still be very satisfactory. And when I'm saying that it will be satisfactory, there won't be any kind of changes. Even though there will be two different types of formulas, iterations might change. Okay, it might be that in fewer iterations over here you get result. By using 2 by n, you will be taking more iterations. But it's still that we'll be able to reach to the convergence. That's something that you are going to have the guarantee. But yeah, that's y cap minus y, the output of the dj dy cap. After that, I want to take the derivative of this y cap with respect to z2. Now, because this is the output of the sigmoid, I need to know what is the derivative of the sigmoid. Now, that's something I'll be teaching at the end of this session. But for now, I have just kept this as sigmoid's derivative of z2. I have not solved the derivation yet. I have just expressed that this is where the derivative of sigmoid is going to be there. And after that, if I reach to the z2's equation, and if I take the derivative of z2 with respect to why, what is the output? The output is a1. And that's why, if I scroll down over here, you can see that the output of this is a1. And now guys, because you're having three different things, how are you going to multiply is going to be an important thing to know over here. It could be matrix multiplication or element-wise multiplication. So now you can decide on this with respect to the shapes that you are having in all of these things. If I talk about y cap minus y, we know that y cap and y both are 4 cross 1. I have told you that the output that we'll be getting over here will be 4 cross 1. So even the prediction will be 4 cross 1. So both of them are 4 cross 1. And if I take the subtraction of that, so that subtraction will also be 4 cross 1. And if I talk about the sigmoid's derivative of z2, that's going to be 4 cross 1 as well. And then the a1 is 4 cross 4. So now, remember that in the matrix multiplication, the rows of the first thing should be equal to the, I should say the opposite way. The columns of the first thing should be equal to the rows of the second thing. In the element-wise multiplication, both the shapes should be exactly the same. So over here, because over here and over here the shapes are exactly the same, I have used the element-wise multiplication. As compared to over here, I have really not thought about this and what kind of multiplication will be over here. But because see, over here the output of this multiplication will also be 4 cross 1 because it's an element-wise multiplication. So the output shape will not change. So 4 cross 1 output is over here. This is 4 cross 4. Now what can I do? See, I can do the matrix multiplication if the output of this is getting multiplied with this in the reverse order. And that's what I've done over here. I'm just calling my D2 as the multiplication of both of these things. And we know that the shape of this is going to be 4 cross 1. So if I take this 4 cross 4 and then keep this D2, which is 4 cross 1, now the 4 from the column of A1 and the 4 from the rows of D2 are matching. And now we can have the matrix multiplication over here. And in no way the shapes were same, so we cannot perform the element-wise multiplication over here. So that's how you can basically remember this kind of things. But it's not that you have to remember this. This is just for the understanding purpose. But yes, that's how your dj dwhy equation is going to look like. Just note that this d2 is nothing but the element-wise multiplication of the error term and the sigmoid's derivative. Don't really worry about the sigmoid's derivative. The formula is straightforward, but how do you derive that also is something that I'll be covering at the end of this session. After this, we are left with the derivative of cost with respect to wxh. And just like how we did for why, that from j we went till y, then from y we went till z2, and then from z2 we went till why. Now if I talk about wxh, it's going to become the derivative of the cost with respect to y cap, and the derivative of y cap with respect to z2. Now, derivative of z2 with respect to a1. If I do why again, I'll again end up getting this thing. But because I want to go till x edge, now I take the derivative of z2 with respect to a1. And now from a1 with respect to your z1. And finally, from z1, you go to wxh. So that's how you're going to get the derivative of activation 1 with respect to z1, and then derivative of z1 with respect to your wxh to be your final thing for your chain of dj dwxh. And that's what we have done, guys. And all of this, remember, are the partial derivatives. Now over here, the two things that we have already seen is the multiplication of the error term and the sigma derivative. And that's what we are calling it as d2. Remember that. So here is our d2 term. After that d2 term, we are having this why term, sigmoid derivative of z1 term, and the x term. So how did we get these three things? Let's understand that part. So if I take the derivative of z2 with respect to a1, the output is why. That's why why over here. Then if I take the derivative of a1 with respect to z1, it will be simply the sigma derivative of z1. And that's why sigma derivative of z1 is seen over here. After that, the derivative of z1 with respect to wxh, which will be simply your x. And that's why you are having x over there. Alright. So that's how we have got the whole output on the basis of this chain rule. And now the first two part, the shapes are already aware about because of the previous thing that we have done over here. And then is also we have marked this as d2, and that's d2 what you are seeing over here, that it is 4 cross 1. After that, we have the why. So it is 4 cross 1 and 4 cross 1 over here also. You could have performed the element wise multiplication as well. But then you also need to keep in mind the final shape of dj dwxh. It should be 2 cross 4. So to get that particular shape, if you do the element wise multiplication over here, that's not really going to work. And therefore, what we are going to do is we are going to do the matrix multiplication. But now how will it happen? It is 4 cross 1 over here, 4 cross 1 over here as well. You simply take the transpose of the why. So if I take the transpose of why, rows and columns interchange its position. So rows will become columns, columns will become row. So over here, 4 cross 1 will change to 1 cross 4. And therefore, successfully, we'll be able to have this matrix multiplication. After this, we are left with this sigma derivative and x. So let's first talk about the sigma derivative. The output of this, guys, if you know, will be 4 cross 4, the 4 from the d2 part, and then the 4 from the transpose of why part. So over here also 4 cross 4, over here also 4 cross 4. You can go with the sigma, not sigma derivative, what am I saying? You can go with the element wise multiplication or the matrix multiplication. But again, the shapes of the output are really important. Therefore, having the element wise multiplication is going to work like a charm, and therefore we are going with the element wise multiplication, and therefore the output of this thing will be 4 cross 4. And let's call this as d1 part. So d1 is 4 cross 4. Now 4 cross 4, you are having multiplied with 4 cross 2 such that the output is going to be 2 cross 4. What can you think about it? What kind of multiplication I can do over here? So the output is 2 cross 4. I can take the transpose of this x so that it becomes 2 cross 4, and then I can multiply that with the help of matrix multiplication with this d1, so that 2 from the x and or I should say 2 from the x transpose and the 4 from your d1 will be the output, that is 2 cross 4. And that's exactly what we have done over here, x transpose matrix multiplication with d1, and therefore you have the 2 cross 4. And now you might be having this kind of a doubt that why exactly this is 2 cross 4. Well, if I show you over here, the shape of wxh is 2 cross 4, and therefore to update this wxh, you need to have a term over here with the shape of 2 cross 4. Only then you will be able to do this kind of subtraction operation over here, or else subtraction won't happen successfully. So yes, that's how we have covered up both of this kind of derivatives of cost with respect to why first and then the wxh. We covered hy first because that is pretty much easy as compared to what we are having it for wxh part. And just think like this, guys, if you are having multiple hidden layers, the number of equations will keep on increasing. Yes, and therefore even the number of parameters. So you always need to define your architecture in a way that even with the less amount of parameters, you get really great outputs. All right. So yeah, we are finally done with this equations derivative of cost with respect to the model parameters. Now we can simply go ahead and substitute it in the gradient descent formula to update the WXH and WHY value. Just in case if you're going to add bias, you also need to perform these steps for bias. And now that you are aware about how this kind of equations are going to be made, I recommend you to find it by yourself that how can you have the partial derivative of the cost with respect to bias in both of these equations. All right. But yeah, over here we are not considering the biases, so we don't have to worry about it. Now after this, the only one thing that is left is how can we perform the sigmoid's derivative. So for that, I'm having the last slide. We know that the sigmoid is equal to 1 divided by 1 plus e to the power of negative input. So to differentiate this part, you can either use a product rule where your u can be 1, v can be 1 by 1 plus e to the power of minus x, or else you can use the quotient rule where your u is 1 and the v is 1 plus e to the power of negative x, and that's what I'm using over here. I'm using the quotient rule of derivative to differentiate this part. And what is the quotient rule? So for that, you simply need to take the derivative of the top part multiplied with the bottom part, so that is u dash v, and then you have the subtraction to the derivation of the bottom part multiplied with the top part as it is. So that's your numerator of the quotient rule. If I talk about the bottom part, it's simply the square of the denominator in the u by v. So that's the quotient formula. And if I implement this over here, you can see that the derivative of 1 will be 0. That's why 0 is written. The derivative part of the bottom will be e to the power of negative x multiplied by minus 1. And therefore minus e to the power of negative x has been written. Because of the negative sign in between, that's what the numerator is going to look like. And now for the denominator part, it's simply going to be the square of this bottom part, 1 plus e to the power of negative x square. And now if you try to solve this negative negative becomes positive. You have e to the power of negative x in the top part. In the bottom part, you are having this. So that's it, guys. That's the derivative of the sigmoid activation function. But now, just so that our computation is going to be very much easier to do, I am just doing one more step. That is, I'm converting this in the format of sigmoid itself. So while computing my derivative of sigmoid, computing them, it will be very easy. Okay, but even if you don't do this step, even that it is fine. Only in the coding part, you will just use this kind of formula instead of this kind of formula. But yeah, if you're interested about this, I've just done one thing, that how can I change this into the format of sigmoid. So if I do this thing, that is 1 divided by 1 plus e to the power negative x. And then if I multiply this with 1 minus of the same thing, if you then try to do the LCM part and try to convert it into a single fraction, that's what you're going to end up with. So you can try to check this by yourself. Do 1 minus this term, whatever is the output of that, multiply that with this particular term itself. And that is exactly what is written over here. The output must be what you are seeing over here. So yes, guys, this were the whole understanding about the mathematical part that you need to know over here. But yeah, in the next video, we are going to start with the computation of everything. And trust me, guys, knowing all these kind of equations is going to help you make that particular part very easy to understand. So that's the end of the video over here. I hope you were able to understand the derivations of the backward propagation equations. And just in case, if not, it's completely fine, guys. There is no need to worry about it. It's just that my motto over here was just to give you this kind of a fun aspect, that you are at least knowing that where exactly you are getting this kind of equations from. Nothing more than that. Now in the next video, we are going to start building the whole architecture from scratch. So stay tuned for that.